Hello, Mr. Kumar, Dr. Kumar,
Yes,
can you
sir,
hear me?
yes, sir, yes, sir, yes, sir.
Okay.
Yes, sir. Thank you, sir. Good afternoon, sir.
Good afternoon. Your voice is coming a little low. Let me try to put my headphone on.
Is it no? It is okay, sir.
Just 2 minutes.
No issue.
Vaibhav, are you there?
Hello.
Yes, sir, yes, sir.
Hello.
Yes, sir. Is my voice audible, sir?
Yes, it's audible.
Okay, okay.
Okay. Acha, can you give me 2 more minutes? I'm
Yes,
sorry.
yes, sir, yes,
Two
yes,
more
yes.
minutes.
Yes, sir.
Yes,
Yeah,
yes.
yeah,
I
please
will
take, sir.
just give me 2 more minutes.
Okay, sir. Okay, we will start at 1:40, sir. No issue. Okay, sir. Vaibhav, is my voice audible to you properly?
Yes,
Your voice is coming little low. Maybe this morning I forgot to connect my microphone. That's why. Yeah. Okay.
Hello.
Yes, sir. Yes, sir. Yes,
Uh,
sir. Yes, sir.
Mr. Kumar,
Yes, sir.
Dr.
Yes.
Kumar.
Yes, sir. Yes, sir. You're audible, sir.
1 second. It's muted. Uh,
You are audible, sir. Are you able to listen us? Listen me?
I cannot
Yes,
hear
sir.
you somehow. Yeah, now I can hear you. Okay.
Is it okay, sir? No? No, is it
All
okay?
right. Sorry for the delay.
No, no, it's okay, sir. Shall I start, sir?
See, again, I am not hearing you.
There is some problem in your side, maybe, sir, in speaker or something like that.
Hello?
Yes, sir. Yes, sir.
Hello?
Yes, sir.
Hello?
Hello. Yes, sir. We are able to listen, you, sir.
Hello? Hello?
Yes, sir.
Hello? Hello?
Yes, sir. You are
But
audible,
I am
sir.
unable to listen you. I don't know why. Hello? I was able to listen you a minute back.
Sir, is audible, sir. Sir,
Hello?
is audible.
Sound
Yes,
is
sir.
not
You are
enough.
audible, sir.
Hello?
Yes, sir. You
Yeah,
are
yeah.
audible, sir.
Yeah, I was unable to hear you. Now I can hear you.
No, is it
Okay,
okay, sir? No, is it okay?
good. Yes, 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 yes. Now this is good.
Maybe some issue in your speaker side, sir. Just you fix it. That will be good.
Ha ha ha. Yes, 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 yes. Now I think it is fine.
It is
Yes,
fine, sir. Okay,
yes,
sir. Okay.
yes, yes. Okay.
Will I start, sir?
Yes, yes. Please go ahead.
Okay, okay. Thank you so much, sir, for accepting our request to be one of the speaker or to give your lecture in this session, sir. So, warm welcome to all the participants and speaker for today's session. So today we have with us Dr. Kaushik Basu. He is a senior member of IEEE. He has received the B degree in electrical engineering from the Bengal Engineering and Science University, Singapore, India in 2003. The MS degree in power electronics from the Indian Institute of Science, Bangalore, India in 2005, and the PhD degree in electrical engineering from the University of Minnesota, Minneapolis, USA in 2012, respectively. He was a design engineer with Cold War India, Bangalore, India in 2006, and an electronics and control engineer with Dyno Power Corporation, South Burlington, USA from 2013 to 2015. Currently, he is an associate professor with the Department of Electrical Engineering, Indian Institute of Science, Bangalore. He has authored and co-authored of several technical papers published in peer-reviewed journals and conferences. His research interests include various aspects of the general area of power electronics. Dr. Basu is the founding chair of both IEEE PLS and IES Bangalore chapter. So once again, thank you so much, sir, for accepting our request and a warm welcome in this session. So now I'm handing this session to you, sir. Thank you so much, sir.
Thank you, Dr. Kumar, for your kind introduction. Uh, I will try to share my screen. Let me just end this. It is telling me now presenter, but this browser does not support sharing. Switch to desktop app. Oh, or use the latest version of Chrome. Okay, so
Possible to open through browser app? Is it okay?
no, actually, I am using this Firefox.
Okay, okay.
No, the Safari. That's why it is not happening. Maybe shall I try Firefox?
Yes, yes. You can check
Sorry,
once.
try that. Mm,
Shall I make you co-host, sir? In that case, if you are able to share, no issue if you want.
uh,
Shall
maybe
I?
we can try that
Okay, yeah.
once.
Just I am
We
trying,
should
sir.
try it.
Just I have given you permission as a co-host. So now you can check. Is it possible from your side?
No, still it is staying switch to desktop app. 1 second, man. I'll try or desktop app or use the latest version of Chrome or Firefox. I'll try Chrome one.
Okay, okay. Yes, sir. Please check, sir.
I should have tried once this before, man, with you. Sorry.
Okay, no issues, sir. Okay, please take your time, sir.
Okay. Can you hear me now?
Yes, sir. Yes, sir. You're audible.
We will. Now let me try to. Can you now see my screen?
Yes, sir. Yes, sir. It is visible, sir.
Again, the sound is.
Yes, sir. We can see your screen, sir. Your shared screen, we
Right,
can see.
right. You can see my screen, right?
Yes, sir. Yes, sir.
Okay. So today, talking about the aging of electric vehicles, right? Current status and future prospects. It's not why it is not changing. Okay, now I can change. Okay. So you can see my screen clearly now, right?
Yes, sir. Yes, sir. Yes.
Okay. So today, what we'll be doing is we'll look into the DC fast charging of electric and what is DC fast charging is often like right. So obviously you have a traction motor and which is which converts the DC power and power motor, right? And of course, you need a charger to charge your battery on the grid or the right? Now we measure energy stored in the battery is like your liters of in your petrol. The battery is about 9,000 rupees per kilowatt hour, and the energy density approximately 3 to 5 kgs per kilowatt hour with today's technology. No, it is not changing. typically right? And because and approximately capacity hours is 50 hours size that kept, right? They are also approximately 300 hour, and but when we look at the reviews, we saw you go only to 16 kilometer approximately, like, which makes sense, right, from this calculation. And then if you have a 50 kilowatt hour battery, what will be the weight of this battery, right? I told kilowatt hour, the weight is about 3 to 5 kg. So it will be close to 150 to 250. You can approximate, let's say, 200. Now, if you take again a mid-size sedan, right, the weight of the car, Swift Desire, right? The weight of the car will be approximately 1200 kgs. So pretty heavy. And what about the cost of the battery? I told you, right? It is approximately 9,000 rupees. So again, if you take a 50 kilowatt hour battery, just simply the cost of the battery is close to 4 to 5 lakhs, right? So a mid-size sedan car sells in India, petrol car, I think the cost of the car itself is about 5 lakhs, right? 5 to 6 lakhs, the starting models. So you can see that still today, with the battery technology, it has improved so much that now you can put a battery inside your car and carry it, and there are cars commercially available, but you can see that still the cost of the battery and the size of the battery is pretty high, right? But this is okay. I don't know, I have trouble changing the slide. Okay, now.
Yes, sir, your voice is also breaking sometimes, sir.
Hello,
Yes, sir, your voice
my
is
voice is
also,
breaking.
yeah, sometime.
Sorry, this is. You can stop me whenever something is not clear. Okay, I can repeat. I think the connection is not that great. Let us take a look at the fuel, right? So how is okay, okay, then we'll do this. I will do a full screen. That you can use is 50 kilowatt, and it will take 1 hour charge the 50 kilowatt hour battery, right? So this time into this power is this energy, right? Comparatively, if the charging rate is 5C, right, then you can use a 250 kilowatt charger, and then a 250 kilowatt charger. Here is could be 20. 1 hour. About it, it takes 1 hour to fully charge or refuel your tank, right? Compared to this, a petrol car can simply do how much? It takes 5 minutes, right, to charge, to refuel your car, right? Less than 1 kilowatt, even if you are running fridge and all that, right? So that means 50 kilowatt is a power that can power actually 50 households, right? So it's a lot of power. So naturally, this charger will be heavy and big, and it will add to the cost of the car. Low power, right? And it will take you close to 7-8 hours, right, to charge the battery, right? So they are good for overnight charging at home. But if you have to charge them fast, you need they are kept out of the car, and they are called off-board charger, and they can directly connect to the DC port of the battery. So now we still have seen that even with a high power charger, 50 kilowatt charger, by the way, now you have commercially fast chargers. Let's say in India, it is available from Delta and some more companies. Now, even with a 50 kilowatt charger, you can see it is taking 1 hour of time, right? So the 1 hour is a long time. See, even with 5 minutes charging, you can see that if you take your car to a petrol pump, right? Uh, there are a lot of cars waiting there. If you are you this charging speed depends upon the battery chemistry. So today there are battery chemistries like so that means already we have seen with today's technology, uh, 10 to 20% of the weight of the car is the battery weight, right? So with LiTO, the weight is much higher, and so it is not viable to put the battery on your car today, till today, and also the cost is much higher. Hello, hello, somebody.
Sir, continue, sir.
Okay. So, by the way, you can stop me and ask me a question, okay? If you have any, no problem. You don't have to wait till the end. And so the but people are working on solid state like technologies, right, to make this happen, right? Reduce the weight, specific weight, and also the cost of these battery technologies which allow you to charge at a faster rate. But then if you look at the charger, right, now the charger power also has to increase, right? I cannot have a 50 kilowatt charger, as I told you, right? A 50 kilowatt hour battery, if you want to charge it in 12 minutes with a 5C charging speed, the charger rating will become 250 kilowatt. Now 250 kilowatt is a lot of power. It is it is the power of 250 households, right? So the thing is that we need to develop this big power electronic chargers, right? So here you see some of the big chargers from Tesla and ABB. I think I need to ABB and all. So ABB has made a 350 kilowatt charger, right? But there is another problem with this higher rate of charging. So higher the power means higher the current, and higher the current, this is DC current, right? And higher the current means the cable will become heavier. So the DC cable that you need to connect your battery with this charger will become heavier. And what happens is that at 400 volt, if you are at 200 kilowatt charging, the weight of your cable is high enough to cross the safety limits, right? So that means, by the way, today, as you can see here in this table, most of the batteries are in the range of typically the nominal voltage range of 400 volts. This we are all talking about four-wheeler, right? Four-wheeler, bus and trucks. So they are in the range of in the range of 400 volts. But this supercharging or extreme fast charging is not possible at 400 volt. So you need to bring down the current. So that means if you have to charge at, say, with a charger of 350 kilowatt of power, the battery voltage has to become 800 volt. So there is a current trend in the industry is now to make the battery voltage go up from 400 volt to 800 volt to support extreme fast. They are also, so now somebody is manufacturing this DC fast chargers, manufacturing these batteries, right? So you need to have a standard connectors to connect these chargers and the batteries, right? See, this is more like the case of your chargers and your cell phone, right? You should be able to use a standard connector, right? Like the Type C that we are using now more and more, right? So here I have listed down few of the commonly used uh, connectors, right? Like Chidem is here, and the current rating and the power that can be passed through these connectors. And you can see that most of the connectors, they can support voltage upwards of close to 1000 volts, right? Many of them. And they can also support current so that they can support DC fast charging in the near future. I don't know why it is not changing. Okay. Okay. I understood the trick now. Fine. All right. So that's good. So now comes this concept of charging station. Now, a lot of people think that, okay, because I need to just simply plug in my electric vehicle to the utility, I can plug it in anywhere, right? But the problem is, as you can see, for DC super fast charging, right, the power is quite high. So you don't get just an outlet can support even say 50 kilowatt. That is the standard today, right? So you need dedicated connection. So if you have few of these cars charging, quickly it can become a megawatt amount of power, right? So now, if you need to provide a megawatt amount of power, you need to connect it to a medium voltage AC grid, 11 kV MVAC grid. You need some medium voltage transformers and switch gears, and then uh, bring it down to 415 volt 50 hertz LVAC and connect your cars, right? So definitely this requires a dedicated charging station. Also, look, if you are suddenly putting 3 4 cars, right, of each say 200 kilowatt, suddenly it's a more than a half a megawatt of power you are drawing from your distribution grid, right? That's a sudden large amount of power, right? And that can easily destabilize your distribution system. So the idea is that if you have a charging station, you can schedule the charging of each vehicle, right? And that way you can reduce the burden on the grid, and also you can reduce the rating of the medium voltage transformer and switch gear, which turns out to be one of the largest and expensive component in the entire charging station. You can also use some local storage, and I think this is not optional. You have to use some local storage, so you can store the energy into these batteries when not many cars are charging. And when you have a large car load here, you can supply some part of the power energy from this local storage, right? and that way also you can unburden the power that you are drawing from the grid and keep the rating of the medium voltage transformer and switch gear lower, right? Of course, uh, what is the point in vehicles? Because we don't want to burn fossil fuel or the gas or the gasoline, right, to stop greenhouse gas emission, right? That is the whole point, right? Why we want to move towards electric vehicle. But if you are charging your car batteries from the grid where the power is actually generated from some coal-fired plants, right? Then what is the point? Why we should do that, right? So it all makes sense if we can charge these car batteries from a renewable source. So, in the charging station, one should also integrate, say, solar panels, right, to power this. So this is how typically a modern charging station should look like. And again, because you have multiple cars charging here, it is also possible, if you don't want to burden the grid so much, then you can actually do, say, if you have a car which is has a very low amount of charge and you want to charge it faster, but you have a car which has a full charge, and maybe the owner doesn't want to remove this car right away, you can provide some amount of the power from this vehicle to this vehicle, right? So this is called the vehicle to vehicle idea. And of course, because there are so many cars with large batteries charged, right? It is a big storage of energy. So in case of a grid instability, you should be able to do some ramp rate support by pushing some amount of energy stored into batteries into the grid when there is a frequency instability, or there is a voltage instability going on in your grid, right? And that is called vehicle to grid technology. But of course, this vehicle to grid or vehicle to vehicle, these are, much more in the future. But certain architecture like this, right, is a reality. uh, uh, am I audible, Kundan? Hello?
Yes, sir, you are audible, but voice is cracking, sir.
Yeah, I think there's some problem with the. I'm sorry. Uh, that please feel free to stop me and ask me if something is not clear. Okay,
Okay,
no
sir.
problem, no issues at all. So, so the thing is that, and even if you are not talking about super fast, extreme fast chargers of 250 kilowatt or 300 kilowatt, even if you have 50 kilowatts, right? So if you put 4 or 5 cars, it easily become a 300 to 400 kilowatt station, right? Which is a lot of power. Probably this can power simply a village, right? Or much more than a village. So, this is a little more detailed architecture of DC fast charging station. So you have your MVAC grid followed by a step down, right? Makes it a LVAC 450 volt, 415 volt low voltage AC grid. And then your renewables and your car and the storage, they are connected through first AC DC converter, followed by an isolated DC converter, right? Because in says the solar, the power is generated at DC, and then you have an isolated DC followed by a AC to DC inverter, and here you need a AC to DC rectifier, and then have your DC charger connecting it to the car. In fact, today the 50 kilowatt are available, even the fast chargers integrated inside the box, right? And they do connect to a LVAC 415-volt grid. So this is sort of the state of the art, and many charging stations which have been demonstrated or in commercial use, the one that I'm showing you in this slide. So here is an alternative. So here you have your medium voltage, you have your step down transformer, making it a 415 volt 50 hertz grid. And then what you can do is you can just put a grid tie inverter or a rectifier, AC to DC converter, and convert it to a 400 volt to 800 volt, a 400 volt DC, right? Or a 800 volt DC, because I told you, the trend is to go 800 volt rather than 400 volt, right? So this is essentially a DC microgrid, right? And now the renewables, the battery was AC here, so we always needed a AC DC converter or a DC AC converter, right? So now when you are charging from the solar to your battery, or you are charging from the local storage, you have two additional conversion stages here because of the rectifiers and the inverters, right? That you can avoid. So if you can avoid that, that means you're saving in terms of cost. It also means that you will be saving in terms of efficiency, right? You can avoid the losses that will happen in those conversion stages, right? And also, another interesting thing is that because you already have isolation with a medium voltage AC grid, right? This DC-DC converters need not to be isolated. But of course, because there is, we all know that the renewables, particularly solar, has a strong capacitive coupling with the ground, right? Solar panels has causing them to ground faults and EMI conducted EMI issues. You may still need an isolated DC-DC here, but most likely the DC-DC converters here in the storage and also in the battery can become non-isolated. And immediately if it becomes non-isolated, the efficiency becomes much better, right? The complexity of the converter comes down and things become simple, right? Also, the interesting thing is that because now it is on a DC microgrid, the control or the overall control or the energy management here is much easier compared to when you have a AC coupled system. But one of the big major challenge in the DC connected system is the protection, because all our, in case of a fault, right, you need a breaker to trip. Now, in case of an AC, the breaker can easily trip at the zero crossing of the voltage current, right? So this is an issue. People are working on this, right? But looks like that this DC connected system is going. People are putting this kind of charging stations together as we speak. But this system, right? This system is not still very common. There are demonstration projects, but we think that this is going to be the future, right? Any question? Can you hear me? Does anyone has any question? So I think if you don't have any question, I will tell you a little bit about the converters that are being used in this system, because I'm telling you, right, this is the this is the state of the art. So we will, if we have time, we will go into this little bit. So for this AC to DC converters, right? The most commonly what you do, you use two-level inverters, right? The six switch standard two-level inverters, and each of them is at a power. It is right, particularly the commercial designs, they still use phase shifted full bridge based converter, right? Phase shifted full bridge based DC-DC converters, and of course in that case the power is unidirectional. You cannot do vehicle to grid type of application or vehicle to vehicle type of application. But the DC-DC here, where the storage is connected, that has to be bidirectional, right? So phase shifted full bridge based converter can be used for the isolated DC-DC the for the car battery. It used for the renewables, right? Because here also power is only unidirectional. It is always coming from the solar panels into the grid, the LV grid, right? Water that is connected with the storage, which is acting as an intermediate energy reservoir for this charging station. That guy should be, the power flow here has to be bidirectional, right? So when you have excess energy from the renewables or there are no cars, you can charge your storage. And when renewables are not there, say you are at night, and also there are a lot of demand of cars here, and you don't want to draw that much power from your MBAC grid, then you will be able to supply the stored energy that is in your locally storage battery to their cars, right? So this converter has to be bidirectional. So the three-level inverter, T-type, neutral point clamped, or the regular two-level inverter, as we know, they are all bidirectional, right? So they can support power flow both AC to DC, DC to AC, right? But the DC-DC converter here has to be bidirectional. But here the DC-DC converters, as I have indicated, has to be only unidirectional. So that is why most of the people, they do use phase shifted full bridge based converter in these two DC-DCs. And here, lot of the design use two DC-DC converters, one in each in one direction. Also, a phase shifted full bridge based converter, and also some designs they are using dual active bridge based DC to DC converters, which I will discuss in more detail later in this presentation. By the way, also in recent designs, people are using LLC based DC to DC converters, LLC resonant based, which are also unidirectional, both for connecting these renewables and also the battery. But the problem with LLC is that, so what are the problems? The problem with LLC is that they actually give you very good performance for uh, when the voltage conversion ratio is not that wide. But both in case of a solar panel and also in case of this battery, right? The battery voltage from full charge to the minimum charge goes through a huge voltage change. And so is the case as you are doing MPPT on your solar panels, right? The voltage that you see, the open circuit voltage to the voltage that you are doing the MPPT, that voltage also changes quite significantly with the irradiation as the day passes by. So LLC type of DC-DC converters are good for a voltage conversion ratio when you don't have a lot of line regulation, what we call line regulation, right? The voltage conversion is fixed voltage conversion. But when you have a larger voltage conversion, then there is a problem, right? So still phase shifted full bridge converters are used for these guys. And for here, you have to use either two phase shifted full bridge converters, or you need to use a dual active bridge based converter, which an isolated DC-DC converter which supports power flow in both the direction. By the way, in some designs, people do use also Vienna rectifiers, which are essentially a 3-level AC-DC converter, unidirectional power flow, right? And where you need only 6 active switches. Maybe we will discuss a little bit about them towards the end of this. But here, when I am talking about this DC connected system, the AC-DC converters, right? They could be of higher power, few level inverters, or either 2-level inverters, or you can use 3-level inverters. And if the power beyond half a megawatt, you may use multiple such AC-DC converters in parallel, right? You can do both AC-DC parallel, then that way you can operate them and still achieve a high power. And as I indicated, that this is DC-DC converters can be non-isolated in that case. But of course, with the solar, you want to use a isolated DC-DC converter. So for solar, you can still use your phase shifted full bridge converter. But for this, the charger, the DC-DC charger for both the storage and the EV battery, you can use non-isolated DC-DC converters. You can use basically half bridge, and which is a bidirectional isolated DC-DC converter. You can parallel several half bridges and operate them in phase shift, right? That is also possible, and people do use that, right? So that is also another possibility. When the power is high, you can share the power between the legs, right? So that's another thing. So this is sort of the state of the art and what is happening. The DC connected systems are also in play, but they are a little bit futuristic, and still most of the systems are AC connected. Any questions? Okay. So now I will start talking about more advanced stuff that is such connected system. What we have seen is that here you have your MVAC grid, which is say 11 kV, three phase 50 hertz grid. And then you have a line frequency transformer, a 50 hertz transformer, which is stepping down the 11 kV to 415 volt 50 hertz three phase AC right here. And then you have your AC to DC converter, right? Or your three phase converter, right? Which will make the DC grid for you. Now, typically the power flow, if you are not talking about vehicle to grid technology, which is still not ready, because most of these charging stations, of course, they are connected in the distribution side of the power system. And in the distribution side, you don't inject power. If you do inject power, a lot of things, the protection, planning, everything goes haywire in in case of in power system. So, and this EV load that we are talking about is large amount of load, right? So still, even though people are talking about vehicle to grid, but still the vehicle to grid idea is great, but it is still not in practice, right? See, utility will not allow you suddenly to inject 100 kilowatt into the grid, because that will cause voltage instability. Now, and of course, problems in metering and many other things, cabling, many other things, right? So power flow, what I'm trying to say, the power flow in these systems is typically unidirectional. So the power is typically still in this problem flowing from MVAC into the DC grid. Now, if you look at the efficiency of this system, the efficiency of AC to DC converter, right? If you use the most advanced IGBTs, right? Fourth generation IGBTs, right? You can switch them at say 5 to 20 kilohertz in that ballpark. And here we are talking about 800 volt DC, right? And let us say AC-DC converter operating somewhere around 250 to 300 kilowatt, right? The peak efficiency that you can easily achieve with a proper design on this inverter is in the ballpark of 98% with the silicon IGBTs. And if you use a silicon carbide, which is of course more expensive, you can switch it maybe close to at 50 kilohertz and still achieve an efficiency close to 99%. Silicon IGBT is close to 98%. And look at the step down transformer, right? People have worked on these transformers on last 100 years, right? So these transformers are very efficient, and uh, you can expect an efficiency of 99%. So is the efficiency of this system from the low frequency and DC grid tied rectifier, right? Here, the power, the efficiency is close to 97%. So this part of the system is highly efficient. But what is the problem? The problem is the low frequency transformer. So if you just take a half a megawatt, right? A half a megawatt step down transformer is going to be very heavy. And in fact, in that AC connected system that I just talked about, right? This AC, I'm sorry. Okay, in the AC connected system, this charging system, right? This medium voltage transformer and the switch gear accounts for is probably one of the most expensive and one of the largest component in the entire charging station, right? Think about it, like if you have to install these charging stations in our crowded cities, right? You need to, you don't have that big of a footprint, right? And you cannot afford to have such big transformers in your charging stations, which will occupy most of the space, right? So what is the alternative to it? So now the size of the transformer is inversely proportional to its operating frequency, right? We all know this, right? So if you increase the frequency, the operating frequency of the transformer, you can reduce the size of the transformer in a dramatic fashion. So here is an example, right? So this is a 100 kilowatt transformer, which is 60 hertz, and this is the same transformer operating at 20 kilohertz. So this is what we call medium frequency, because at high power, you may not be able to switch more than 20, 30 kilohertz. So this is 20 kilohertz, right? And you see this transformer weighs about 35 tons. Look, 100 kV weighs about 35 tons, right? And we are talking about 1 megawatt, right? So that we are talking about 350 tons, right? So very, very heavy, right? And the same transformer here weighs about 450 pounds, right? Just 450 pounds, right? So this is 150 times lighter. So you increase the frequency from 60 hertz to 20 kilohertz, and the weight of the transformer got reduced by 150 times. Because you now have low amount of copper and iron, your eddy current, your copper loss, though they also do reduce, and the efficiency also that they have found in this case was increased. Actually, this is taken from a report from Los Alamos lab, and I got this from Professor Mohan, University of Minnesota. So the thing is that if I have to take two things from this slide, first thing is the size of the transformer is one of the limiting factor in realizing a compact charging station in the busy crowded cities. And you can reduce the size of the transformer by increasing its operating frequency. But we have to remember, whatever we do to replace this low frequency transformer, the efficiency of the system has to be also high enough. Because the state of the art system with a low frequency transformer and an AC/DC rectifier, the efficiency is in the ballpark of 97%, which is highly efficient, right? So this is some alternative ways to do this, to realize the high frequency transformer. So what is being done is that, you see, this is your medium voltage grid, right? Here in these two projects that we are talking about, the grid is not 11 kV, they have used 3.6 kV grid, right? And then they have AC/DC rectifier, right? It's an edge bridge converter, right? And which converts this 3.6 kV AC to this DC bus. Here is 7 kV DC bus, right? 6 to 7 kV DC bus. And then what you have here is a bridge that converts this 7 kV DC to a 20 kilohertz high frequency AC, and then you pass it through this transformer, and then this side bridge rectifies. Now the voltage is low here, you step it down with this medium frequency transformer, right? And here you rectify with this bridge, and the voltage becomes 400 volt DC this side. Now you see the transformer is now in this configuration. Now see, again, I am making from medium voltage AC to a low voltage DC with an isolation, right? And the main step down is done by this medium frequency or high frequency transformer. But look, this medium frequency or the high frequency transformer is actually now operating at 20 kilohertz and not at 60 hertz. So its size will be very small. What are the difficulties with this system, right? What are the problems with this system? By the way, this project was done by North Carolina State University in 2014, and the power rating was somewhere around 10 kilowatt. And this is done in ETH Zurich by Professor Kollar's lab. And here the power rating was about 25 kilowatt. And they used in the high voltage side, right? They used high voltage silicon carbide MOSFETs. NCSU used 13 kV SiC MOSFETs from Cree, and Professor Kollar's group used 10 kV MOSFETs to support a 7 kV DC bus here. But what are the problems with this setup, right? So anyone wants to comment on this? Because thought that it will be a little bit interactive. Can anyone tell us what are the problems with this solution? Kundan, can you hear me actually? Am I audible?
Yes, sir. Yes, sir. Now you are properly audible, sir.
Okay. So any of the participants wants to comment? I guess that our participants are from the power electronics area, right?
Yes, sir. Yes, sir. They are from all over the Indian institutes faculty. Some are from institutes. Some are from industry. So most of the participants are faculty, sir, with different
Right.
areas. Not maybe different areas, not proper power electronics, but all are mostly faculties.
Power and power electronics areas, right? So the thing is that anyone wants to, find out some problems with this setup or with this solution?
Maybe, sir, at the end they will ask if
Okay.
you can
Okay.
carry on, sir.
Okay.
Yes.
Okay. Okay. So the thing is that here you see that first of all, to have to support a 7 or 8 kV bus, right? I need to use this 13 kV or 10 kV silicon carbide devices, which can switch, at high frequency. Yes, yes, which can switch at 20 kilohertz. But where are those devices, right? So these are actually experimental devices which are not in the market, right? You cannot find them in the market. They are experimental devices. They are not foolproof, right? So it is very difficult, right? So you cannot commercially realize this today. So that is one of the problems. The second problem is if you do switch this, let us say at 10 or 20 kilohertz, right? As they did, you are switching 10 kV or a 7 kV at 20 kilohertz, right? So think about the DVDT, right? Think about how much EMI this thing is going to generate, right? That's also a big challenge. And another problem is that you need to also have these capacitors, which can, uh, which can withstand this high medium voltage, right? By the way, the thing is that they used the NCSU design used a dual active bridge converter. These are half bridge dual active bridge converters, and the design from ETH they used uh, series resonant converter, as you can see here. Both of them used LCL filter to connect to the grid, and also look, they only worked on a single phase. They didn't make any three-phase converter because of the obvious reasons, because it's already so complicated. In this design, they used a LC kind of snubber to, sort of limit the DVDT that is being generated across the pole, so that you can solve little bit of the EMI issue, or the EMI or the ground currents or the high frequency currents that will get injected into the MBAC grid, right? So this is sort of the direct approach, but we have a lot of problems with this approach. So the alternative approach is to go for a multi-level configuration. So here it is, right? This is the most common generalized diagram. So what you do is you focus first on this cell. So here you have this medium voltage three-phase AC grid, right? And this side you have the low voltage DC grid, low voltage DC that you are generating, local grid that you are making. So what you do is you make this cells, right? What is there in each cell? You have a AC to DC power conversion. So this is basically an H bridge rectifier, like in your previous slide. So this previous slide was also that, right? You have a rectifier, single phase. You have a rectifier followed by an isolated DC-DC. So that transformer here is operated at a high frequency, which is dropping down the medium voltage DC to a low voltage DC, right? So that is what here. So you have a AC-DC, single phase AC-DC followed by an isolated DC-DC. So now what you can do is each of this AC-DC module, let us say if we use 1200 volt devices here, right? The DC bus can be 800 volt, right? But with 800 volt, you cannot support an 11 kV here, right? So, but what you can do is you can cascade these cells, right? And you can take a multi-level approach, right? So where you put so many cells here so that each unit sees a voltage which can be supported by an 800 volt bus here, and you can use your regular 1200 volt devices, 1200 volt IGBTs, right? Or silicon carbide MOSFETs, right? So that is the idea, right? And then what you do is on the AC side, because it is medium voltage, you parallel all of them, you connect them in series, and in the DC side, you parallel all these converters, right? And make a common DC bus here. So that is basically the idea, and this is what we called a multi-level input series, output parallel configuration. So you not only series all the DC in the same phase, you can also series all the DCs coming out from each phase with all three phases and make a common DC link, right? And then you can connect your chargers with isolated DC-DC, isolated DC-DC chargers to the batteries, right? So this is basically the idea, and a lot of universities and companies, they did make this, right? Here again you can see North Carolina State University, Virginia Tech, um, EPRI. This is a national lab in US, and the Delta Electronics. They have made this converter. They have changed what they used for the AC/DC. Some AC/DCs are unidirectional, like they have put a PFC type of configuration, power factor correction circuit with boost converters, right? And some are using only regular H bridges. And then you have this isolated DC-DC, right? In the isolated DC-DC, what they do is they use dual active bridge, or somebody uses LLC based conversion. They used also parallel units, right? Again, series on this side, parallel on this side, right? So many different configurations. And the voltage level at which the testing or the design was done is in the ballpark of 1.6 to 13 kV. I think 13 kV is the maximum one built by Delta. And then the voltage level is, um, just a second. Okay. Hey, Kundan, hello. Can you hear me?
Yes, sir. Yes, sir. Yes, sir.
Hey, there is a problem here, man. I am in an university, right? From
Yes,
where I
yes.
am doing this.
Okay, sir.
So there is a famous actor, some Punit Kumar has died here, it seems,
Okay,
and
sir.
the government has put this 141,
Okay, sir.
144, section 144, and it seems that if I don't leave now, I will not be able to reach home.
Okay,
So
sir.
what shall I do, man?
Uh,
Uh, can
it's
we do this another time? I mean,
this.
I have another half an hour left.
Okay, okay. No, no, sir. It's okay. You can conclude in 5 minutes, sir. And if there will be some
Okay.
questions, if you will be possible to handle, otherwise we will forward you in mail, sir. Okay. So if
Okay,
something,
okay,
okay. So no
okay,
issue, sir.
okay. So maybe
We
then
can
in
conclude it before, sir.
a few minutes I can conclude. I have almost reached to that stage, like what people are doing, right? The
Understood.
overview part,
Okay,
right?
okay, okay, sir.
Okay, 5 minutes I can.
Yeah, yeah. You concluded in 5 minutes, sir. No issue, sir.
Right,
Okay.
right.
Thank you, sir.
Okay, okay. So then okay, so then this is what people have done in last 5 6 years, right? From all of these places, and the power rating remained less than 50 kilowatt, right? I will go full screen. Power rating remained less than 50 kilowatt. So this is what is happening, what has happened. But you can see that I will tell you some of the limitations of this. That you can see that you have this capacitor here, right? So now this capacitor here, it is single phase, right? And here, so here the power is DC. So this capacitor has to take the second harmonic ripple. So it has to be electrolytic. And you can see, so these are large capacitors. And you can see there will be so many capacitors because there are so many cells here, right? So these capacitors are also not reliable, so they reduce reliability, and also these capacitors are large, right? So they actually reduce your power density. And so this is one of the limitation, and you can see there are so many modules here, right? It's a complex, complicated converter. Both there are a lot of signals are required. There are a lot of issues with this, right? So that is why they have not become yet commercially viable. Now we are working on this to simplify some of these things, solve some of these things. I will show you. So this is one converter that we have recently published in the ECC conference that happened this year. So where we don't have this DC link capacitance, this is actually a low frequency capacitance. Sorry, it's a high frequency capacitance, right? And you have a unfolder circuit here, which is operating in line frequency to make the single phase AC to a rectified AC. And then we have a dual active bridge based conversion here, right? And there is no DC capacitor here, and because we connect all the three phases together, we don't see any pulsating power, and so no electrolytic capacitance on this side, right? So you can look at our publication here. Soon this will be on the IEEE Explore. So, and then this some of the advantages of this that I just told you. I will skip these things. And then I will little bit tell you that in our lab we do a lot of hardware development. So you can see this is a silicon carbide based modules that we have developed, which can switch up to 100 kilohertz, and each of this is a hub bridge, and they can actually process about 5 kilowatt of power in a hub bridge configuration, right? And they can they can do a 800-volt DC bus, right? And they are completely modular, right? You can both electrically and mechanically seamlessly you can connect and make different converters. So here is a controller that we developed with Zinc. So so Zinc is a controller from Xilinx, which has two dual core ARM processor and a FPGA fabric connected through a high speed communication link. So you can generate complex, do a lot of complex stuff with that. So this is that with a launch pad. This is the interface card of the controller. So with this, we can generate about 40 optical PWMs, sense 18 analog signals, and all that, right? and this is some experimental result. And then here I will very quickly conclude. So we have understood that you need a 50 kilowatt hour battery for a 300-kilometer range sedan car, and what we have to reach is a 5C charging speed so that we can charge it in 12 minutes. But we need a 250 kilowatt charger, DC charger. This is a heavy big charger. So we need to go to a concept of charging station which has to handle a megawatt amount of power, and we need to integrate storage and renewable to that. And medium voltage DC charging station offers an efficient solution because they don't have those intermediate AC/DC stages. And high frequency transformer based MVAC to LVDC rectifier can dramatically reduce the size and the cost. And in this work, we are working on an efficient and compact DAB based single stage multi level architecture with high frequency link rectifier. And I am really sorry, man, I need to leave now. Okay, but I think you got the picture, and I think you guys enjoyed.
Yes,
Hello.
sir, yes, sir, yes, sir, yes, sir. Thank you so
Okay.
much, sir. Yes, sir. It was really very informative. Initially, it has some issue with the mic problem, but overall it was okay, sir. And we have really learned lots of things. Thank you so much, sir, for accepting my request. And if participants, if you have few quick questions, you may ask, or else you can write to me. I will forward to
Right,
professor.
right. If they can email you,
Yeah,
then
yeah,
I
yes,
can
sir,
I
yes.
can answer those
And sir,
questions.
I would request you, sir, kindly you share your PPT later on, sir. If you have
Yes.
some personal data, you may edit that one and you can send me, sir, later on. Okay,
Okay.
sir.
Thank you very much, Kundan.
Thank
Thank
you
you.
so much, sir.
Thank,
Thank you so
thank
much
you.
for your presence,
Bye
sir.
bye.
Thank you. Bye, sir. Take care, sir. So, participants, thank you so much for your kind presence. So, I will be sharing the link for your test. That will be start from 3:45 to 4:15. So, it is 30 minutes exam. So, kindly give that exam. That is necessary for your certificate purpose. You have to secure 60% marks in that test. So please submit your Google answer sheet on or before 4:15. Okay. So please make sure that you are submitting your answer on or before time. And we'll start our valedictory function at 4:30 p.m. Okay. So thank you so much for your kind presence. I will share the exam link on your mail as well as on your WhatsApp, on the FDP group WhatsApp group. Okay. And kindly join at 4:30 p.m. for valedictory function. Okay, thank you so much. Do you have any query, question you may discuss if you have any point to discuss? If you have any questions, you may put in WhatsApp or in mail. That will be more better regarding today's talk, this session talk, because professor is not with us now. But we can forward your question if you have really any question for each session. Okay. Thank you so much. Any query, any question to you? If you have any query, you can tell me. Kindly try to submit your answer sheet on time. Okay, answer on time. Thank you so much. See you at 4:30, and before that, I will be sending the Google link for your exam. Thank you.